Yeah, I think we can start.
Hello everyone, this is Embedded 101, so we'll get started. Okay, I'm Darsh, I'm a SIGPwny helper and, yeah, okay. I'm Darsh, I'm a SIGPwny helper and an embedded lead. I'm a CS plus philosophy major with minors in informatics and math. I was involved with embedded since ECTF 2024, and I'm not very good with fun facts, so a fact is I helped lead the creative writing club.
Okay. And I'm in, again, previous SIGPwny president. I'm in the BSMCS program. I've been in the embedded team since 2023. And fun fact, I just paid $50 to cheese the Seesaw challenge yesterday. So real quickly, some announcements, and we're actually really excited about this. So Fall CTF 2025 is in less than a week. So it's this Sunday, or this coming Sunday. If you sign up at sigpwny.com/fall CTF, you'll get a free shirt, you'll get free pizza, and very cool, you'll get one of these badges. This is actually just a dev board. It actually looks a lot cooler in person. But it has an ESP32 chip, microcontroller that has Wi-Fi capabilities. It's got, a very nice color display. It's got piezo buzzer, joystick, and buttons. So I highly recommend you guys go to Fall CTF. If not, if you don't really care about the CTF, that's fine. But go pick up a badge because there's a good chance that our next meeting will be using some of these badges, and we'll have extras for those who can't make it for whatever reason. But the next meeting we'll be doing some more hands-on microcontroller programming, and so the badges that we have here is sort of a great way to get started with that. But on the topic of microcontrollers, we're going to just jump right into it. So microcontrollers are also typically abbreviated as MCUs or microcontroller unit. The MCU glues everything together in an embedded system. So in an embedded system, you usually have peripherals like a display or a speaker. And so that's useless if you don't have some sort of control logic, which transforms inputs into outputs or does business sort of logic and things like that. MCUs are typically fully packaged. So what this means, and you've probably heard this term before, is it's a system on a chip, which means it's got everything in it. So it's got CPU cores, RAM, some flash to run code. It's usually very lightweight, super power efficient, because again, with embedded systems, these are embedded into things in the world. So you're likely not going to have a lot of maintenance of those devices. Or maybe you're in somewhere with less power. So it's very important that these are sort of power efficient. And because of that, you'll see microcontrollers have way less specs. For example, you'll have megabytes of RAM as opposed to gigabytes. Your cores will be at a much closer clock speed. So like 100 megahertz as opposed to your laptop, which could be anywhere from 3 to 5 gigahertz as opposed to megahertz. And microcontrollers are meant to be specific purpose. So there's microcontrollers that will do analog processing, digital processing. Most often you'll see MCUs with processing both digital and analog inputs. Yeah, so just to sort of kind of build a mental picture of a MCU, I'm going to steal Apple slides here where they have for example, their M1 chip diagrams, and you can see these are in the Apple events, but they break down each of the components of a CPU. And microcontrollers are just sort of the same thing, except they've got a lot more low power things, a lot more specific things for specific tasks. So again, just like a CPU, you have CPU cores, you have RAM, and you have all these peripherals which will do things. So UART, which we'll talk about in a bit, timers to keep track of time cycles and things like that. Random number generation, I2C is something similar to UART, and etc. And so also another part of the MCUs is they have to interface with the rest of the peripherals, so they'll have pins. This is sort of one of the most common packages you'll see for microcontrollers. And it's slightly different from a CPU, because usually when you think of a CPU, all the pins are at the bottom. There are some microcontrollers which are like that, and those are called ball grid array packaging. But you'll typically see these sort of pins on the side like this. And the pins have various purposes, which we'll get into in a minute. And then this is kind of a quick slide, but I want to just quickly talk about memory. So in your system, you will need to store data. So that's kept in memory. And memory is stored as bytes, and each byte has a memory address. So a memory address is usually some hex value that and that like individually addresses a single byte. So I can write a byte to that memory address, or I can read a byte from that memory address. For those of you that might not be familiar, RAM is volatile memory. This slide is not finished, but volatile memory is basically memory that usually doesn't persist. So if you shut down the system or turn it back on, RAM is usually wiped. And flash memory has the capability of retaining data. So that's non-volatile, which means that it will persist, usually without a power supply. Sometimes there are some types of flash memory where no, that's actually not true. Yeah, it's just without power supply. Okay, and now we'll move on to peripherals. So we talked about microcontrollers, just sort of a very high level overview. Now we're going to talk about why we have microcontrollers in the first place.
Yeah, so a peripheral is pretty much kind of the interesting things that we want to do with the embedded system. So there are two kinds of peripherals, sensors and actuators. So sensors will convert a physical phenomenon into an electrical signal. So that includes like thermometers, which measure heat, and then will provide some electrical signal measuring that. Cameras, which take in an image, and infrared receivers, which also measure heat. And we have actuators, which convert an electrical signal into physical phenomenon. So that includes like motors, solenoids, and like infrared transmitters. And transducer is a general term that covers both sensor and actuator. And so, yeah, we have an example of infrared transceivers, which can both transmit and receive. Yeah. Another peripheral is like the integrated circuit. So it's a semiconductor that integrates collections of electronic circuits, including like transistors, resistors, capacitors, diodes, and many others. And then it controls the CPU functions of an embedded system. So that involves like retrieving and decoding instructions from memory and using those instructions to perform computation for memory and output devices.
And typically, when you have like much lower power systems, you'll have like basically the board just be entirely integrated circuits, because actually for a lot of use cases, MCUs are completely overblown. Like you don't need a lot of the features of a microcontroller. So if you can think of integrated circuits also as being a way to split up like a bunch of microcontrollers, and you wire them up correctly, you'll have a very rudimentary one. And that tends to be a lot more cost effective.
Yeah, and then we also have general purpose input output pins. So most peripherals, like we mentioned earlier, like the UR or I2C or the TRNG, those pins will be reserved on the system. But if you want to sort of modify those peripherals directly, GPIO allows you to control the state of the pins. For example, like turning them on or off, and they're unused by default. But you can you can define and implement a unique purpose using GPIO.
So all the pins on like a microcontroller, as we shown earlier, like most of those will be general purpose input output. Some are like, for the power or for the ground. But microcontrollers will typically come with a lot of GPIO. And typically when a microcontroller advertises a lot of functionality, what they do to sometimes keep the package smaller and improve the efficiency is they'll reuse some pins across some GPIO peripherals. So for example, maybe I want 5 UART, which would require 10 pins. And then if I could be using some pins from a GPIO peripheral, which is unused. Like for example, those pins could also be used for I2C. But a lot of GPIO pins allow you to select alternate functionality so that it's sort of flexible and allowing you to pick the pins that you want to use. Okay. So we're going to talk about how do peripherals communicate, or how do MCUs really communicate with peripherals? Like in this case, we're looking at like MCU to peripherals, MCU to another MCU. or MCU to the world. And so MCU to the world would be something like you would have an actuator which does a sensor, which triggers a motor or something, and does some sort of physical impact. And in order to make sure that like we kind of standardize communication, we use wire protocols. So there are many different protocols, and they all have their own advantages and disadvantages. So for example, I2C allows a host, like a single microcontroller, to communicate to many devices using only 2 wires, which is really powerful because, or sorry, not 2 wires, but like 2 buses. So basically, I just need to connect all the guest devices to the host device on a single bus, and on basically 2 buses, 2 separate buses. And so this is very powerful when you want to like have control a lot of different sensors or actuators at the same time. UART is a much simpler version, but it's only one-to-one communication using 2 wires. But as a result, it's usually a lot more easier, a lot more effective to implement, especially when you're building interfaces which only require one-to-one communication. And another communication protocol is SPI, which is serial peripheral interface, which uses 4 wires. But it offers much faster data rates, and that's good for things like external flash chips, where I can have a flash chip which can have a lot more flash storage in my microcontroller, and I can use SPI to communicate to that to write data, get data, and at faster rates. So I'm going to quickly go over through like UART just to sort of explain what's going on. So as I mentioned earlier, it's only 2 wires, but we actually have a 3rd wire here, which is typically used for ground. So TX in this case means transmitter. So the device will be sending data out of the TX port, and it will be receiving data through the RX port. And so each device sort of looks at the port like in its own respective way. So usually you need to flip the wires, swap the wires in order so that way the data goes in the correct port that's supposed to go into. And each of these wires is considered a channel, and so each channel can send some amount of data. Usually, UART defines that speed as baud rate, which is the number of bits per second. And so you can have traffic basically going both ways at the same time. And the actual protocol of UART is fairly simple as well. So you can sort of see like the line is typically idle high, which means it's usually like some sort of voltage. And in order to start a UART transmission, you just pull down to ground, and that will indicate a start bit. And then basically each of the UART peripherals will sync on that start bit pull, and then it will start reading. It will start sampling at some set frequency or some set rate in order to read the data bits. And so there's also a parity bit which helps potentially correct data if there's some interference in the wire. And then usually you have a stop bit which ends the transmission and says like we're not doing any more transactions. So the most common UART configuration is 8 data bits with no parity. In this case, this diagram does have parity, and then 1 stop bit. And usually you'll have a baud rate of 115,200 or 9,600. So clearly the one is faster than the other, but the 9,600 one is like sort of like one of the most popular ones because it's been around for so long. But nowadays it's going to be like that faster one that you see there. And there's a link here if you guys are interested on reading more about how UART works. But I'm going to do a quick demo right now. So right here, I have a microcontroller that's connected to my computer. And it's connected via USB cable. Now, most microcontroller boards will have a USB to UART adapter built in. So if I were to plug this device and if I were to open a serial console on my laptop, I'd be able to communicate over UART, and the UART would be going through these USB cables. For some reason, that's broken on my system, but that's fine because what we're actually going to do is we're going to connect this logic analyzer. And a logic analyzer is basically something that allows you to, it's kind of like a passive device. It sits on a bus and it listens for the digital signals that are being transmitted over the wire. And you can collect those signals and decode them. So what I'm going to do is I'm going to connect this back on. And I will exit this to bring up logic. So that's disconnected for some reason. I'm gonna swap these devices. This is looking like that. Oh, here. Live demo. Okay, there we go. So so right now I have two channels running at once. I'm going through this. If I click play, you can see there's two signals. One's actually high, one's low right now. It's just kind of confused because it doesn't know what's supposed to be what. If I plug in the microcontroller now, you want to see very quickly so some flashes go by. So I'm going to stop that. I'm going to pause. We're going to backtrack a bit. And we can see that when I plugged in the device, there was power on the ends here, and it actually sent some signals. So this is what UART looks like, right? So you got your start bit, you've got 8 data bits. So if I wanted to send like, I forgot the exact ordering, it could be that high as 1, it could be that low as 1. It's one of the two. But you want to send your bits like this. If you have like a repeated bit, for example, then you just hold it down for longer. And you can see there's these little dots, and these dots are representative of what the sampling is. So we're running at 115,200 baud rate. So that's the current transmission rate. And logic actually decodes each of the characters that's being sent by the signal. So we can actually view this sort of pane here, which is this analyzer view, and it shows like all the signals and their information. We can also do this terminal view, which will put all the ASCII characters together. So it prints out some things. Now normally this is the line, which this bottom line is actually connected to UART transmit on here. So it's connected to UART transmit because it's sending the data out to this channel 1 here. If I were to be sending stuff from my computer to this device, you would see data on channel 0. Unfortunately, my computer won't deal with this properly right now, so we're not going to use that. But this is just sort of a demo of sort of showing like what logic analyzers are, which we'll talk about in embedded 103. But I also wanted to show off like UART and kind of that information. Does anyone have any questions? Yeah. So yeah, I actually preset it. So I clicked on this like add analyzer and this async serial. So you would configure like all the data transmission rates here. So like right now I set to 15200. If I were to set this to something like slower, like 9600, I click save. It will not, yeah, as you can see here, there's like this error, it says like framing error. That means like something went wrong. But it actually still sort of decoded. Because in a sense, actually, I don't even know if that's correct. No, it didn't. This is just a secondary output. But yeah, logic is a cool tool to like do wire protocol analysis. And these logic analyzers are actually quite cheap. This logic analyzer costs like $12 off of Amazon, but there are some the company that builds the software like sells some more expensive ones like for $500. and those come with like fancy things like analog signal decoding.
Yeah, okay, so to control the peripherals, we need software and firmware. So the difference between software and firmware is like we have software that's like programs run by the computer, and on like your laptop or your PC, that's typically managed by your operating system, which has a lot of overhead, but it provides some system security as a result. Firmware is just software for hardware, and it can be run with bare metal access, which means there's no OS managing code. So this is more efficient because, as stated earlier, operating systems have a lot of overhead, but at the same time, it can be potentially less safe since you don't have the same guarantees that the operating system is offering.
The other thing to know about this is that if software crashes on your operating system, usually it's fine because you can just run the software again, and your entire operating system usually doesn't crash. If your firmware crashes, it's going to crash hard because there's nothing backing it. It's kind of doing its own thing. So again, potentially less safe, but because there's no overhead of running an operating system, it's much more efficient.
So, yeah, we mentioned earlier that like we have all these communication protocols that allows the microcontroller to control the peripheral. So we have UART peripheral for UART communication, I2C for I2C communication, and also like TRNG for random number generation. And so these peripherals are mapped to reserved memory addresses within the MCU. And software can control peripherals by reading and writing values to these memory addresses. Yeah. And so to figure out how to like actually write to a specific like embedded systems peripherals, you have to essentially just consult their datasheet. So for this year, ECTF 2025, we have the MSP M0 L2228. So if you like look up that name plus datasheet, you'll be able to find this PDF. And you can see it's like this is table of contents, but has like a lot of information about pretty much everything in the microcontroller. So if we want to actually focus on what do you call the peripherals, we can go and we can see this is the memory organization. So yeah, we can see that how each memory region is organized, and we can see like sort of the address, the range of the addresses within each memory block.
So SRAM is just another word, just basically your standard RAM in a microcontroller. So this is where if it's doing something, if it needs like temporary variables, it's going to store that data in that specific SRAM memory region. So like for like the 228, like you'd expect all that RAM to be in these within these address ranges. And if you have actual code which runs on the firmware, so there's like two different flash banks for that. So they have a specific region and addresses where your code would be found. So when you're executing instructions, they're going to be read from these memory addresses.
Yeah, so this is like a table that has all the peripherals mapped to their base address. So let's say we want to specifically work with the UART, right? So UART 0 has this memory address, and so we want to figure out how to use it. Yeah, so we go to the registers within each UART, and we try to see what fields it has. Yeah, so it accepts like text data. Yeah, so as you can see, there's a lot of information. This is just the single UART 0 peripheral.
Yeah.
And you can see there's way more. The table on the peripheral summary is incomplete as well. So there's a lot of information about every embedded system that you can like find on the datasheet.
But basically, as we were mentioning, in order to control peripherals, you need to read or write from the memory mapped input output. So each peripheral will have a base memory address where all its registers can be found. And then you find a list of registers, and then you figure out the fields in each register. So as an example, data sheets in action, I like to call this, because this is like sort of the raw version of writing like code to run on a microcontroller or to do something. So this is sort of like a for loop. It's going to take your string hello world, and then what this for loop is doing is it wants to send data to your output. So the microcontroller will take a character and it will process it when you send it to that character to some memory address, and then it will write out the little signals that we saw earlier. And so like usually you can just do like write directly to some address in order to start sending out characters. However, there's a lot of things you need to do. Like for example, you don't know what this does because I put a generic memory address, but what this will do is it'll check like, oh, can I write this to this address? Like, because sometimes I could have a lot of bytes being sent at a time, and the microcontroller is like, yo, chill. I can't handle this at once. So please read this memory address before you send me anything else. So that way I'm ready to send it. So again, manipulating peripherals like UART is just reading and writing values to some memory addresses. And you're looking at this code and you're probably like, I hate this. And you're right. Oh yeah, sorry.
Wait, no,
Yeah, back to memory side like this.
the one,
Yeah.
like, in the OS at least, like, some of this RAM would be like, or some of the memory would be like kernel space or user space.
Yeah.
Does that distinction exist in embedded?
So there are microcontrollers which do have this distinction. And so like, for example, the ARM Cortex M3350 series, those will have something called ARM Trust Zone, which is where you have you can switch between like a kernel, like a root user space and a user space, and that provides like privilege boundaries and separation. So that does exist in some microcontrollers. However, most microcontrollers you find don't have this abstraction. So if you see a memory address, it very likely is just a physical memory address for like the whole system. So
So like code can manipulate itself, or it can manipulate one of the code banks as it runs them.
it could, yes, right. So like if you have a peripheral, so usually like with these so that's actually sort of a lie. With the code flash banks here, like the data in the flash is usually mapped to these addresses, and if you write to these addresses, it won't do anything because it's just mapped. There are some peripherals where you'll have a flash controller, and that flash controller, if you write to that memory address in a certain way, it will allow you to reprogram the flash. But that's also sort of dangerous, right? Because you have code that's sort of writing itself. So actually, that's a reason why you have two flash banks here. A lot of microcontrollers will have this, where basically you have sort of a backup region to execute off of, and so that like you have like one that's like a current version that you're running, and maybe you want to upgrade this flash bank one and now start running that, and so you can always like restore back to a working version of firmware. Yeah. So directly manipulating GPIO is basically like, you with a little switch on like a wire. If I can sort of explain that.
Running through the memory addresses more efficient than.
Yeah, because like the microcontroller is like the hardware logic is programmed so that when it sees something being run into memory address, it will run the action for you, and it's usually more efficient because a lot of the times like
These are.
like usually, yeah, it's influenced in the hardware. So there's also a distinction which we'll talk about in the future when we do embedded probably 102 or 103. But basically, like I could take control of the raw pins and implement a UART state machine in software. So basically, I'll constantly be checking, oh hey, did this pin turn on? Like let's say, I had a UART signal which was transmitting data, right? I need to be constantly checking the state of the GPIO pin like at the same baud rate, and then if like there's a start bit, now I need to start reading sampling to figure out my data bits. And so doing this in software is what we call bit banging, because you're just like taking the raw bits and you're like banging them together like I don't know, like a ham like a monkey with a hammer. But most microcontrollers will have like dedicated state machines in the hardware, which will keep track of this for you. So because of that, like you're not like wasting your CPU cores trying to process UART or something like that. And it's just done in the hardware automatically. So the nice thing about the memory map input output is that you just send something to this memory address and the hardware does it for you. Or you read something from this memory address that the hardware is giving you. So this has just sort of been how computing has been. Like this is exactly how your computer works as well. When you're running code on your operating system, usually like a normal program doesn't have access to like peripheral memory regions directly, because otherwise like your software could do really bad things to your hardware. And so that's the point of the operating system that manages all the peripherals for you. And the same concept applies where if it wants to do something with the hardware, it's going to write to memory addresses. And if it wants to read from hardware, it's going to read from memory addresses. Does anyone have any other questions? Okay. So again, this kind of sucks because like I'm like writing all this boilerplate code just to write a character to UART. Although this would be a lot more difficult to do in software, right? If I was bit banging, like I'd have to have like all the flows to like set the GPIO state, read the GPIO state, and have like a infinite loop to read out data, and it'd just be a mess. So this is just with, you know, using the memory map IO on a microcontroller. And so to make this easier, you'll have hardware abstraction layers, which are basically libraries which directly translate like some of those like hardware memory addresses into functions you can call. And then software development kits are basically like building on top of the hardware abstraction layer. So usually SDKs will include additional code like cryptography libraries or code to control external peripherals such as displays or LEDs. Those aren't necessary to program the microcontroller, but like SDKs are like kind of packaging a bunch of things together to make your development experience a lot nicer. And so you don't have to like manually program a lot of things, you just call some functions. So again, would you rather like this code we're like writing and doing this loop check for UART, or you just have a nice function you call to write something out? So this takes in a string and then it will send something out. Again, this is abstracting away a lot of information. Like you wouldn't know if this was checking, you wouldn't know if this function was checking for like potential overflows, unless you read the code or you read the documentation. So by using hardware abstraction layers or software development kits, you're simplifying the process, but you're maybe there's a certain point of granularity that you want, right? Like, because if I abstract away too much, my embedded device starts becoming a lot less efficient because I'm not thinking about things like maybe memory management or like specific things to do. So firmware development is about finding the right balance between these two. And you don't want to like overly abstract, otherwise the code that becomes useless. So that was a short meeting, but next Monday we're only talking about microcontroller programming. So what we're going to do is we'll have the badges available, and if people want to do some more advanced programming, we'll have these Texas Instruments and the Max 78000s available as well, and you'll program like C or Rust. But for the badges, that will actually be in MicroPython, which is like Python for microcontrollers. So hopefully that's relatively straightforward. And we'll have sort of activities that like do like print hello world and GPIO controlling GPIO peripherals. Yeah.
Speaking of MicroPython, or rather, not a MicroPython, do you know a way to like get C SDKs for the same type of stuff that MicroPython does? At least for like Raspberry Pis, because I haven't been
Well, usually you have the C stuff first before the Python. So
that's what you think.
yeah. Raspberry Pi definitely has like some sort of C++. They definitely have a Rust hardware abstraction layer to program like Raspberry Pi stuff. But that's usually unheard of, I feel like. Like you don't usually program microcontrollers in Python because again, like this is sort of that same question about abstraction, where now you have to run sort of the Python interpreter, sort of, in your microcontroller. Not really, but I like to think of it like that.
Oh, is your always one streamer, or sometimes you'll have like multiple, like yards and all like, communication will be in parallel?
So yeah, you can have multiple UART peripherals, and they can be connected to different devices in an embedded system. But at its base, it's going to be a 2-wire protocol, and it's 1-on-1.
feel like do the people who make microcontroller like provide you with like compiler infrastructure for everything? Like is there like an LVM backend and right cluster?
Usually, no. Like compilers people and microcontrollers people are like pretty separate. So what people will do is they'll add support for compiling for an architecture to a compiler. And so most microcontrollers will support some specific instruction architecture. All the compiler has to do is take code and build it for that instruction set. Yeah?
No, just
Oh. Oh, sounds good. Yeah. Yeah. Does anyone have any other questions? Okay. That's it for this meeting, but hopefully definitely come to the next meeting. That'll be a little bit more exciting. We'll have a lot of hands-on stuff there.
For some reason. Hi. Next one, I think you're open. Yeah.
right OS programming.
What's the last one?
Yeah, you do that. I'm usually see all these last. I like it. It seems
Yeah.